Okay, so our last topic is called work. Like a lot of topics in here, we start with a simple concept and then we make it quite a bit more complicated. So it starts with a simple idea that work is determined by force times distance. And frequently, that concept of force is related to weight. So for instance, if I pick up this chair, and this chair weighs, let's say, 20 pounds, and I lift it a certain height, I'm doing some work on that chair. As I lift the chair, the weight of the chair doesn't change. It's going to stay that number of pounds, regardless of how high up off the ground I lift it. That's the simple part of work. What becomes more interesting, and where we need calculus, is if that weight changes. Okay. So for instance, we have a couple examples that we'll work through together, but if I pick up a leaky bucket, and I start to lift that leaky bucket, as I lift it, the amount of water in the bucket decreases, therefore the weight changes. So if the weight of the object you're talking about changes over time, then that's going to create something called a variable force. That's where we need calculus. Initially, we'll start with something simple. Okay, so that's called a constant force. If the weight or the force doesn't change, then it's a simple physics problem of force times distance. We, however, want to get into the idea of variable forces. What happens if something changes as the problem goes on? And then, of course, today, since we're talking about force, you should become a Jedi Master in your spare time. Not a lot to ask out of all of you.
And the Sith reason.
Or Sith Lord, yeah. I mean, I would encourage that. I mean, I feel an obligation to go to the light side. Light side. The good side. What is it? The dark side and the
Non-dark
side. The non-dark side. Right. I remember Luke using that phrase a lot. Yoda, I want to be part of the non-dark side. Non-dark side. You should stop. All right, so constant force, like I said, it's really simple. We're going to take force times distance, capital F representing force, D representing distance, W representing the amount of work done. We're going to look at all kinds of different forces. Centrifugal, electromotive, that sounds fancy, gravitational, and the one that Luke and Ray use.
Man, you're really killing those references.
I'm pushing the whole force thing, aren't I? Wait till you see the one example involving lightsabers. It's going to be a good one. Okay. As I already mentioned, the weight of the object will be considered the force in many of the problems, not all of the problems, but some of them. Okay, so simple problem. This is a constant force, like I said. If I take a 50-pound weight and I lift it 4 feet, as I lift that weight, the weight of the object doesn't change. It stays 50 pounds. Therefore, it's just force times distance. Okay, 200. Boom. Done. Those are foot-pounds, by the way. Those are the units. Those are cool. Foot-pounds. Feet times pounds. If you move in inches, you would have inch-pounds. If it's, kilograms, then you have meter kilograms. Or, kilometer tons. No, that wouldn't work, because that's pounds. I don't want to combine the metric and the imperial system. That's major faux pas. Any problems there before I move on? So simple, it doesn't even worth, it's not even worth talking about, even though we already have it. Now, let's talk about variable force. What changes in the problem? Okay, so we're going to break it down into small ideas like we did with a lot of the other stuff, like finding the volume of revolutions. We turned it into little slices. When we did all kinds of fun things, most of the time we're going to calculate what it requires to move something a short distance. There are some exceptions to the rule, but in general that's what we're going to do. And since it's a really small value, you'll recall in calculus, small values we represent with a dx. Okay, easy peasy. Yep. Beautiful. There's our little equation. Work is equal to the integral of a to b of f of x dx, where f of x is the force. For a lot of times it'll be the weight. And dx is how far we're moving that little guy. And And then we integrate. Why do we integrate?
It's calculus.
Because it's a calc class, correct. Different sweater, I'm okay. I'll answer my own question. The integral accumulates all the distances that object will move. Calculate small distance and then add up all the small distances, because as it says there, it accumulates all those pieces of work. That's Robert Hooke. He worked with springs.
That's so fast.
That's what people do.
Yeah, I don't know.
Like of all the things to get into, his thing was springs. We're a judgment-free zone here. And Robert Hooke, which I'm sure you learned in physics, yes?
Yes.
What did Hooke do?
He made a law.
Hooke's law. He made a law. Because like all idiot mathematicians and scientists, they name it after themselves. Okay, so Hooke's law says that the force on a spring is the spring's constant times x. Isn't it? So we're going to calculate how much work is required to stretch springs or compress springs. They're the same thing. We're just going to move a spring around. This is what Hooke did for a living. Yep, that's why he got all the chicks. Yeah. All right. 12-pound force is used to stretch a spring from its neutral position. Do you understand the concept of a neutral position on a spring? You hold the spring at the top, you just let it hang there, however far it hangs down is the neutral position of the spring. You can either compress it or you can stretch it. We're going to stretch it. So that spring hangs down 8 inches and we stretch it to 11 inches. Then we're going to figure out how much work it takes to stretch it from 8 to 13 inches and then from 10 to 13. Ooh, we're going to move away from the neutral position. What piece of information don't we know about these blue springs? The spring constant, correct. So we can calculate the spring constant. The spring constant K. We know in the problem it says it takes 12 pounds of force to stretch that spring how far? 3 inches. From 8 to 11, 3 inches. Therefore, how big is K? 4. 12 divided by 3 is 4. Nice, easy spring constant. It doesn't matter what you do to that spring now. From this point on, it has a spring constant of 4. And I'm sure you've seen all kinds of different springs. Springs in your watches, springs on your garage door openers, springs in pens. Good. Mattress.
Well, some of them.
What'd you say? I couldn't hear you with that carrot in your mouth. All right, what was that? Do you still have a carrot? Good, moon shoes. Yeah. Robots.
No, they have like the band.
They have monsters. Monster trucks have springs in them. Yes. Cars in general have springs in them. Did you? I didn't hear you. Usually I just. Trampolines have springs. Very nice. Okay. All right. So we want to know how much work does it take to stretch it then from 8 to 13, which means we're stretching it from 0 to 5. Now why 0 to 5? Because 8 is the neutral position of the spring. That's what we consider 0. Even though it has a value of 8, we consider that as being at 0. And so we get that easy little integral. Because Hooke's law is Kx. We know what K is. We solve for that for these particular blue springs. Dx is how far we're going to stretch that little guy, and then we stretch it from 0 to 5, or we're accumulating all those little units of work from 0 to 5. How would it change for part B when we're stretching it from 10 to 13? Say again? 2 to 5, correct. Okay. So 50 inch-pounds, notice the units here. And then part B, we're going from 2 to 5. That's the only thing that changes. And so you get 42 inch-pounds. Springs are fairly easy to work with. It will get a little bit more complicated, especially when we get to the lightsaber example. Nope. It's 4 because we solved for the constant, the spring constant, which was 4. And then that goes into the KX. KX for that spring.
Oh, it's this.
Yep, correct.
Oh.
How are we doing so far? Okay, good. Let's lift the weight. Got a weight hanging off the side of a building. It's a beam. And we got a little picture there. So we got an 800-pound weight, and I lift that 800-pound weight up. It would seem like that's a constant force problem. The weight of the beam never changes. It's always 800 pounds. However, that cable that you're lifting has weight. That has to be taken into account. So I start with 20 feet of cable hanging over there, and then I'm going to pull that up. I have a 50-foot long cable that weighs 150 pounds. Therefore, how much does each foot weigh? 3. 150 divided by 50 is 3 feet per pound. Sorry, 3 pounds per foot of that cable. And the weight of that the weight of the beam is never going to change. That's a constant force. So you'll see when I set up my integral, there's the weight calculation for the cable. It doesn't change, and so we get to that thing. The weight of that object at any point in time is the weight of the beam plus the weight of the cable. And how much does the cable weigh? Well, if I haven't pulled any of the cable in, it's going to weigh 150 pounds. But as I start pulling in the beam, the cable weight is going to decrease. Does that 150 minus 3x make sense? I feel like I'm talking too much about something that you just probably understand. All right, so I pull in 1 foot of cable, it now weighs 147 pounds. I pull in 9 feet of cable, et cetera, et cetera, et cetera. So that's the weight at any point in time. And I shouldn't say that. Not point in time. That's the weight after I've pulled in any amount of cable. Time is irrelevant to this problem. You can take all day to pull that thing up if you want. Now what we want to calculate is how much force is done to lift that weight. So we go back to the concept of force times distance. How far do I move that cable? I'm going to calculate what it takes to move it just a little bit. So I get that dx in there. Right, and this is what confuses people. I am moving the cable 20 feet, but what I'm calculating is how much it takes, how much work it takes to move it just a little bit, a dx. And then I'm adding up all those little bits from 0 to 20. I start without pulling any cable in, and I calculate that until I've pulled in 20 feet of cable. So this concept of the weight coming into play becomes very relevant when you're working with large objects, when you have to move large objects. Because even something simple like a nice light cable becomes a problem when you have a large amount of it. That's the hard part. Set it up. That's a fairly easy integral, yes? So I can go through this quickly, right? There's the weight, there's the distance, great, blah, 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 boom. Whoops, 18,400 foot-pounds. If I go back to this, be a little clever here. You can add 800 and 150 right out of the chute. You get 950. Then take the integral, or I should say antiderivative of 950 minus 3x. Those are easy peasy, plug and chug. 18,400 foot-pounds. Now I don't know about you, but I have no idea, I have no basis for work So I don't know, I mean, I assume that's a big work value, but I don't necessarily know. Okay,
Why is it 600? Because if you plug in 0, it would just be 0.
That's the 400.
that's the 20 into the 3 halves minus x squared. 20 times 950 is 19,000. 20 squared times 3 halves is 600. You're right, if you plug in 0, it would be 0.
Yeah.
Okay. We good? What are we doing next? Lightsaber? No, darn it, it's water. Okay, fine. Let's do water. This one changes a little bit, so you have to change your concept of what we're going to do here. Instead of moving something a little increment, we're going to calculate how much work it takes to move a little piece of water and then add up all the pieces of water. A different way to approach a problem. So I've got a tank. It's a conical tank. It has an altitude of 20 and a radius of 4. Now, you have the picture on your paper, but it would be interesting to have you draw this. Conical tanks should probably be upside down. Otherwise, it's not going to hold a lot of water. So it's an upside down cone. And we want to pump water out of it. Now, are there a lot of conical tanks around? Probably not, but it's a good way to start the problem. More practical problem would be like, for instance, you're emptying your swimming pool. Your swimming pool happens to be a conical swimming pool. Yeah, because I know everybody's got a conical swimming pool. Okay, so what I've done is I took a little sliver of water in the middle of that tank. And it doesn't matter where you take a sliver, but I took mine right there. And I called that distance from the top of the tank x. Now, some of this stuff is my choice on how to solve the problem. You could do it differently and get the same answers. So I chose a slice about halfway down. I called its radius r. And I said it's x units away from the top of the tank. If it's x units away from the top of the tank, then it's going to be 20 minus x with the bottom of the tank. You with me?
Yeah.
Okay, good. Now you got to be careful in these problems because sometimes that tank might have a hole in the bottom and you're emptying out of the bottom of the tank. Those values might change. But since I'm pumping it over the edge of the tank, I've decided to define that distance as x. So all of those are choices that I made. We know that the radius of the tank is 4, and we're good to go so far. Density will come into this problem. You know what density is, right? What is it?
What's density?
What?
It was different now.
I get it. It's like a,
Yeah,
it's a bad pun.
it's
Still get it,
It's a
though.
good time.
What did you say?
Okay, fine.
You go like, oh, hey Paul, hey, what's density?
I don't know.
Well, it's Los
Vegas, yeah.
What's
There you go.
density? And they go like, well, I don't know, Colorado, and you have no mass over volume.
You're just wasting time.
I will say that I'm thankful to have this audio recording so that in years to come, I can look back, or not look back, I would listen back at this opportunity and think, that was one of the high points of my teaching career. So thank you, Kaylee.
You're so
I'm just think what would have happened if I didn't hit that record button.
I know.
We would have lost a slice of history. Right. Okay. I've completely lost track of what I'm doing. Thank you, density. So, hopefully you recognize that if it's not water I'm pumping, maybe it's a tank full of oil, maybe it's a tank full of apple juice, maybe it's a tank full of yogurt. If the material changes, the weight changes, and if the weight changes, the work changes. Okay, this happens to be water, which we'll work that into the problem in a second. So the concept here is I'm going to take that little sliver of water. By the way, what shape is that sliver of water?
A disc.
A disc. I don't know why everyone would, it's just a disc, so why not everyone go, ooh? Okay, beautiful. You guys love this, great. That was unnerving. I'm going to calculate the volume of that disc. And why do I care about the volume? Because the volume will get me to the weight. And once I have the weight, I calculate the weight and the distance that gives me the work, and then I integrate to accumulate all those slivers of water. There we go. Okay, that's what I just said. The volume of that thing times the density, since density is mass over volume. See, senorita?
This is not really a math question.
Oh, boy.
Well, it's a physics question. So, you know, if I picked up the 20-pound box, I would be the one, like, I'm doing the work.
Correct.
What is doing the work? Like, what work is getting done in this process?
Probably some motor is doing the work.
Oh, okay.
Whatever you're using to pump the water.
Got it.
Okay. Volume times density, and that's where the density comes into play in calculating the weight of that sliver. So notice that the volume of that disk is pi r squared dx, because I want a really skinny disk. And we've talked about this when we did the volume of revolutions. The density is 62.4. Is that something you need to memorize? Probably not, because it'll change depending on the problem. So maybe it's rocket fuel and has a different density. Maybe it's peanut butter, different density. Those two things together give me the mass of, or sorry, I should say the mass, the weight of that sliver of water. How far am I moving that sliver of water? X. Very good. That'll take it over the edge of the tank, as it says, emptying the tank. Okay. There's the setup. Pi r squared dx is times 62.4 is the weight of the weight of the sliver. X is the distance that we're pumping that thing. And this is in a mess here, so I cleaned it up. I took all the constants and moved it out in front. I left all the variables on the other side because we have to integrate those variables. What's wrong with that integral? Has two variables, that's bad. How do we get rid of one of the variables? Good.
We find out what r is equal to in terms of x.
You got it. Your friend and mine, similar triangles. Oh, yeah. Bam. Whoa, look at that. Okay. 20 minus x, the height of the small triangle, over r, the radius of that triangle, or the base of that triangle, I think, is equal to 20 over r. So big triangle inside little triangle. This pops up all the time. This is why they give you conical tanks, even though nobody uses a conical tank. What that allows me to do is get rid of r's, because now I can write an r in terms of an x, which does complicate the integral a little bit. But thank goodness for fn it. Because now you got to take that r and square it. And we get that. And of course I cheated, because I just fn'd it. Yeah, sure. You could, however, do that by hand. That's not too bad. You square out the binomial, you multiply everything by x, break it into individual terms, take the antiderivative of each one of those, put in 20, put in 0, subtract the 2, multiply the answer by 62.4 pi, and you're going to go. By the way, I will remind you again, 3 decimal places on all answers in AP Calc. Round or truncated, doesn't matter, but you do need 3 decimal places.
Wait,
Yes, sir.
you have the numbers repeating?
Yes, 3 decimal places. Okay.
So what if it's,
So I did that.
so you have to multiply the pi and
You can if you want, or you can leave it. That's an acceptable answer. Yeah, but if you get a decimal answer, 3 decimal places. Okay, now, yes, Amanda.
Okay, so the x at the end of the integral, I know it's how far it's being moved, but how do you know that it's just X?
Because I chose it to be X. That's how I define it.
Okay.
So you might put your sliver closer to the top of the tank, but you're still gonna move your sliver X units.
Okay.
You can put down at the very bottom, it's still X units. Now, what can change in this problem? Suppose I only want to empty half of the tank. What would change in that bottom line? Zero to 10 or 10 to 20?
Depends which one.
I can't let this one go.
Wait,
Okay,
wait.
Tim,
Wait,
let's
no, no.
think about this. I'm with you 100% if we're emptying the top half of the tank. How would you empty the bottom half of that tank?
If the top half is already empty, then you just, then it would be out of bounds.
Defying the laws of gravity.
I don't know, if we find it,
Just let it go, just let it go.
I think you could like pour it out. or
As far
you
as the
could, like-
limits of integration go, as the problem changes and certain amounts are taken out, this is a standard issue. Standard issue where we're emptying the entire tank. If you're only emptying part of the tank, ask yourself, where am I taking X's from and to? So in other words, I'm taking my first sliver at the very top when X equals 0. And I continue taking X's until I get halfway down, which is when X equals 10. So therefore, the answer to my question would be from 0 to 10. If you define X differently, you could do the same problem, but define X as the distance from the bottom of the tank. That's a different setup then. Then you would be looking at taking your first sliver at 10 and taking slivers all the way up to 20. Okay. But the easiest way I found is to define X as the distance you're moving things.
Just based on like the 10 and 20, so the bottom half of the cone has a smaller volume than the top half. So it's like, how would you, it's not like half, it's like halfway down, but not half of the volume of it, more of it.
Correct, so the work wouldn't be identical.
Okay.
Because the volumes are smaller, but the
Yeah.
distance is greater.
Okay.
And you would think that they would cancel each other out, but that doesn't necessarily happen. Okay. Any other questions on this? It's a different approach to some of the other problems. It's not just simply force times distance, but actually is just force times distance, because all we're doing is calculating the weight of that sliver times the distance that it's being moved. But the problem in itself creates a more complicated scenario, especially when the similar triangles are thrown in there. If it was a nice rectangular tank, like a swimming pool, you'd be good to go. Your sliver would be rectangular, calculate that, the distance over the edge of the tank, life is good. We're gonna stop there. I know there's another example on that, but I wanna give you an opportunity to get in and start some of the basic work problems, some of the things we talked about. We'll do the leaky bucket problem tomorrow. We good? Paul brought treat Tuesday. Paul and Ashley, sorry, brought treat Tuesday, so they will get everything set up.